All right, so where I left off last time, I had just made this complicated linear regression model where I'm predicting the highest year of school someone completed based on 3 explanatory variables. So I could kind of designate those x1, x2, and x3 if I wanted to. And I was saying we could write out the equations for each of the versions based on the categorical variable that we've got. So I'd like to just do that. So let's start by writing out the overall equation. So I'm going to be lazy and write y hat as my response variable. If I wanted to be a little bit better, I could write highest year of school completed and then put a giant hat over the whole thing, but we'll use y hat as shorthand. And that's going to be 9.17 plus 0.30 times highest, I'm just going to call it highest father, plus 0.017 times age, maybe I'll just call it age to be short, and plus 0.56 times born in US. So that's the overall model equation. But if I wanted to, I could make 2 different versions of the model, one for born in the US, yes, and one for born in the US, no. So the way that I'm going to do that, I'm going to do one for born in US, yes. For that one, I'm going to plug in 1 for the value. So 9.17 plus 0.30 times highest father plus 0.017 times age plus 0.56. 0.56 times 1 is 0.56. And then we're going to combine together this 9.7 or 9.17 and the 0.56. So then I'm going to get 9.73 plus 0.30 times highest father plus 0.017 times age. And then if I wanted to do the same thing for born in US, no, then I'm going to plug in 0. So it's going to be the 9.17 plus 0.30 times highest father plus 0.17 times age plus 0.56 times 0. Anything times 0 is 0, and so then I don't have to do anything particular there. So then I've got my 2 versions of the equation. I've got this one and this one. And because they each have 2 numeric variables in them, I've got my highest father, years of schooling, and age. This is a pair of parallel planes. So it's 2 parallel planes in 3D space. So I'm going to switch back over to my computer so that I can show you what that looks like. All right, so I've created a little 3D visualization of the points for this example. And I'm making the visualization using R, but the code is a little bit complicated. It doesn't work well on all kinds of computers. It requires more packages. So I'm not going to recommend that you do this code yourself. I'm just showing you the visualizations so you can get an idea of what it looks like in 3 space. So I've got the years of schooling that a person had versus how many their father had versus how old they are. And if I move this around in 3D space, you can see those integer round-offs that we've seen before. So, people typically report that they've done an integer number of years of school. And I think their father's schooling is probably also reported in integer values, and I think their age also is. So depending on how we view it, we can really see those integer values. So one kind of model that we had talked about was just a single flat plane. So I'm going to see if I can get that flat plane to show up here. All right. So if we were just using father's years of education and age as a predictor, then there's my flat plane in 3 space. And if I needed to do prediction of the number of years of school someone had, I would find the point and then I would project down in the direction of the years to do my prediction. So that's what my model would look like, a flat plane in 3-space. But we've been talking about a slightly more complex example, which was a pair of parallel planes in 3-space. So again, I'm going to see if I can get that to go. All right, so here it is. So now I've got 2 planes in 3-space, and one of them is for the people born in the US and one is for the people not born in the US. And you can see they're pretty close together. That value that we had found for the coefficient on that categorical variable, it was small. It was like 0.5 or something like that. So that's why they're so close together. And then, if we were going to do predictions, if I was a little bit better at R, maybe I would have made these points colored based on whether the person was born in the US or not. That's kind of beyond me. But then we could think about which ones we're going to project down onto which of the 2 planes. But that's the geometric interpretation of that model. All right, so I think that we had gotten about to that point before. I don't know if we talked about the interpretation already, but I've got my sort of generic sentence, and if it's a categorical variable, the interpretation has a compared to reference group, we would expect the comparison group to be, and then it's going to be the, like beta 1 hat units higher or lower. So we're not going to have that 1 unit increase anymore for a categorical variable. It's just going to be this comparison. And then for multiple regression, the thing that we add on is at the end, holding all else constant, or holding, and then we could list out the names of the variables. So if we were going to interpret the coefficient on age numeric for a 1-year increase in age, we'd expect the years of schooling to go up by 0.02 years, holding the highest year of school their father completed and their immigration status, born in the US or not, holding those 2 things constant. So we want to make a fair comparison, an apples to apples comparison. So we've talked about this parallel slopes model. I wrote out these equations for you on the iPad. And then we're going to start thinking about some more complex models. So one approach that we could have taken, and this is a bad approach, is to split the data up. So if we thought that there was a different relationship between how much school you've done and the amount of school your dad did and your age, based on whether or not you were born in the US, we could do 2 separate models. So fit the same model, but one time, instead of doing just the full GSS data set, I'm going to filter GSS to just where the people were born in the US, and the other time filter to just where they were not born in the US. So this is not how we want to do it, but just for the sake of argument, I'm going to show you the output here. So if we look at this, all of the coefficients are different. We've got a different intercept, we've got a different slope for highest year school completed father, and we've got a different coefficient for age numeric. In fact, it's so different that one of them is positive and one is negative. So for a 1-year increase in age for people who were not born in the US, we'd expect their years of schooling to go down, holding the amount of school their dad did constant. Versus for the people born in the US, in this case, we'd say for a 1-year increase in their age, we'd expect the years of schooling to go up, holding the highest year of school their father completed constant. So that's a really different sort of relationship. And we'll see how to do models like this more properly when we get further down in the lab. But for right now, we're just kind of thinking about, well, that could break this necessity to have those 2 parallel planes. These are both planes in 3-space, but they're angling at completely different ways. They're not 2 parallel planes. They can sort of move however they want. And I'm not going to write out those regression equations. So if we want to start thinking about these more complex relationships, the way we want to do that is with interaction effects. So I think we've seen this model before, this flat model, which is just a flat plane. But I'm going to make a warped plane as well. So I'm going to run this m flat, and we could just look at the summary, m flat. I think we've seen these coefficients before. And then I'm going to do m warp, which is going to be still trying to predict the highest year of school completed, but I'm going to predict it based on these two things kind of multiplied together, or I'm going to use the asterisk in between them. So if I run that and then look at the summary of m warp, I'm going to see a bunch of coefficients. So I've got a coefficient for the highest year school completed father, one for the age numeric, and then this is the interaction effect, the interaction between the highest year of school completed father and the age numeric. So even though I just told it that I wanted those two variables kind of interacting, I got all the individual coefficients as well. So R does that by default. And I think I'm going to switch over to the iPad just to write out this equation and talk about some of the interpretation. All right, so first of all, let's just write out the overall equation. And I'm going to have to use what I know about R's scientific notation to get these back into a little bit easier to see decimals. So I'm going to call this y hat is equal to 9.5, let's round, plus, and then this one on the highest year school completed father, it has an e minus 1, so it's going to be 0.31 times highest father. And then the next one has a minus 2, so it's going to be 0.018, let's say, times age, plus, and this last one has a minus 5, so it's going to be 0.12346 times, I'm going to just say like h colon a for that interaction. So I think that we know how to interpret the standard coefficients. In this model, for a 1-year increase in the amount of school your dad did, we'd expect your number of years of school to go up by 0.31 years. For every year of age increase, we'd expect your years of school to go up by 0.018 years. And then the interaction between those two numeric variables gets really weird. And I think in this case it's especially hard because that coefficient is it's very small, so it's not practically significant, and then it doesn't have a significant p-value, so it's also not statistically significant, but we still might want to think about how to interpret it. So the way that I usually do this is I'll say for a one unit, and in this case I'll say 1 year, for a 1-year increase in the highest schooling of father, the relationship between the highest year of school an individual completed and their age increases by 0.000068. So it's about the relationship. And I think this one is pretty hard to interpret. I'll try and do one with a categorical variable because I think it's a little bit easier to think about there. But that would be my interpretation. And I think I'm going to swap back to the iPad now and see if I can show you that warped plane in 3D. All right, so this is pretty unsatisfying because the scale of the data is such that it's really hard to see the warping in that plane. Wow, this is really rotating. Okay, so we've got that, but I'm going to try and show it to you. So I'm going to do the flat one first. Fix that. So there's my flat plane in 3 dimensions. That's the perfectly flat one. And then let's try and put the warped plane on there. And again, I want to try and fix that. Okay, so I think it's going to be pretty difficult to see it. You can kind of tell that there's a saddle point there. So I did it in pink, and so it's either dropping away or dropping above somewhere here on those sides. I guess my guess based on the data would be it would be kind of coming up here and under there. But again, really hard to see what's happening because that interaction term was not very significant. So we'll try and do this again when we have a more significant interaction effect.